Okay. Welcome everyone. Am I audible properly? Am I audible? Can you hear me?
Yes, sir.
Okay. So last day I have discussed about the sputter deposition techniques. So now there are other deposition techniques uh, is available, which is called as chemical chemical vapor deposition technique, or CVD. Okay, chemical vapor deposition technique. Okay, and that obviously here the constituents will be some form of chemical, so that's why it is called the chemical vapor deposition. Hmm. Now chemical vapor will decompose to form certain layer, and that layer may be uh, dielectric layer, that may be metallic layer. Okay, and if you use the metal organic compound, then you can get metal film deposition by using the CVD technique. Okay, so CVD technique is very useful and very much used nowadays in IC design, integrated circuit design, and MEMS based device design. And basically is defined as a formation of a non-volatile solid film as a substrate. Okay, and it is happened by the reaction of vapor phase chemical that contains the required constituents. So you have to so you have a chemical in vapor phase which will have that constituents, and that will deposit as a solid after decomposition. Okay, so CVD is an extremely popular and is preferred deposition method for a wide range of materials. Okay, so now before discussing CVD, I would like to introduce one video how the CVD, or what are the components are there in CVD system. So is it visible, audible?
Yes, sir.
Is this visible?
Yes, sir.
Okay, now what kind of materials we use in case of CVD technique? So in using CVD technique, the one is a polysilicon film deposition in polycrystal silicon. You can get using CVD technique. Okay, so that is one application. So dielectric film like silicon dioxide or silicon nitride you can have, and single crystal epitaxial growth, that is also a CVD process. A single crystal silicon is known as epitaxial formation. That means epitaxial means ordered growth you can get using CVD technique metal film deposition. If you use organometallic compound, which just like tungsten, molybdenum, etc., you can deposit using the CVD technique, and these are the various applications. Okay, so now CVD reaction mechanism. So here, what are the reactions? First, transport of the reacting gaseous species to the substrate surface. Then what is the next step? Absorption or chemisorption of the species on the substrate surface. Okay, because those species after transportation you have that has to absorb. Now third step is heterogeneous reaction catalyzed by the substrate surface. The fourth one is desorption of the gaseous reaction and products. What are the byproduct? Desorption should be there. Rest of the gases transport of the reaction. Uh, Products which away from the substrate surface. Okay, so these are the five steps followed one by one in a CVD reaction chamber. Okay, so these are the process. So now this is a simple thermal CVD reactor system. So this is a gas inlet. This is the susceptor on which the wafers are kept and susceptors are heated. Now susceptor means container of the silicon wafer. Okay, so if you heat it, then gas is flown onto the surface of the wafer. Okay, so in this reaction chamber at high temperature, the gas will decompose and the solid material will deposit on the substrate. Okay, here the what are the gases used? One is silane. Silane. Okay, silane ASiH4. This one SiH4 gas form. So it will decompose first at high temperature. Then H2 SiH2 plus 2H2, that is also gas. Then SiH2, it again changes to SiH2 means amorphous, and then SiH2 amorphous will give silicon solid and H2 gas. So solid material will decompose. Okay, so after absorption, uh, 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 then the solid material is coming out and it is deposited onto this wafer. So silicon will be deposited on this wafer. Okay, now deposition reaction occurs at the surface of the wafer. Clear? So now, uh, can you see the diagram properly? Some hazy type diagram. So now there is another CVD technique which is known as LPCVD, low pressure chemical vapor deposition. Okay, so to achieve reasonable deposition uniformity, the process is designed to keep the reaction strictly controlled by the deposition kinetics. So in this chamber, you can stack the wafer. You can stack the wafer in this way. This is the wafer, and these are the heating elements. Okay, here also this one. So these are heating elements. In between there are wafers. Okay, so this is the furnace tube. Okay, the gas inlet here, the gas inlet, you are ejecting gas, means some reactant gases are coming up. This is one reaction chamber. Okay, and one of the advantage of this LPCVD is to prohibit the formation of nucleation. Like I have told you last in my last lecture, nucleation. Okay, uh, so what is the nucleation? Silicon. Silicon, 2 3 molecule together form a nuclear, and that particular particle will deposit onto the wafer. That means uh, that is a defect. We need, if you go for single crystal silicon, we need a ordered growth molecule by molecule, just like building a house by using bricks. But instead of that, if the silicon particles are conglomerated and 2 3 particles together form a particulate, and that particulate means that is a nucleation, and that nucleation stops. So if one defect is formed, that defect will continue throughout the crystal, and that crystal you cannot use in practical system. If you use it at a low pressure CVD, so formation of the nucleation of the particles can be prohibited, can be prevented under low pressure. So this is the low pressure CVD, the technique, and it is much better than the atmospheric pressure CVD, APCVD, atmospheric pressure CVD. Okay, so the pressure must be in between 0.1 to 1 torr. Actually, this pressure reduces the gas phase nucleation. That's why it is used. LPCVD is much better than the atmospheric pressure CVD. Low pressure CVD is much more widely used. So now come to lithography. Again, I need to show you one video. Can you hear the sound of video properly?
No, sir. Sound is not coming.
Oh, so why are you not telling me that in previous video?
Sir, I thought there was no sound in that video.
No, there was sound, but
integrated circuits. Cell phones,
now can you hear the sound?
Yes, sir.
Okay.
computers, televisions, and any high cell phones, computers, televisions, and any high technology product requires the use of printed circuit boards, microcontrollers, or integrated circuits. How are they made?
There is
These
your
devices are extremely small.
file manager is showing, not that video.
Oh, visual not showing. Okay.
No, sir, your file manager is showing.
Acha.
And any high technology product requires the use of printed circuit boards, microcontrollers, or integrated circuits.
Now, is it audible and
Yes, sir,
Yes,
it
sir.
is audible and visible.
okay?
Cell phones, computers, televisions, and any high technology product requires the use of printed circuit boards, microcontrollers, or integrated circuits. How are they made? The components of these devices are extremely small. If they are too small to be seen by the naked eye, how is this possible? These products are made using a technique called photolithography. Photolithography is the process that transfers shapes from a photomask to the surface of a silicon wafer using light. Photolithography comes from the Greek words photo meaning light, litho meaning stone, and graphy meaning writing. Photolithography is printing with light. Alphonse Poitvin was the man who invented the process that is still used in modern micro manufacturing today. He did this in 1855 by combining light with lithography. Just to give historical context, Poitvin invented the process 4 years before the completion of the iconic London landmark Big Ben, not to be confused with Steelers quarterback Big Ben Roethlisberger. The modern process that is used today requires many steps and several different tools and chemicals. The silicon wafer is treated chemically with hydrogen peroxide to remove any contaminations that may be present on the wafer. Contaminations may come from the removal of the wafer from the pods they are transported in, or from the robot arm which the wafer sits on. Then, a layer of silicon is placed on the wafer to act as a masking film. Hexamethyldisilazane, or HMDS, is placed on the wafer to increase adhesion of photoresist to the wafer. This reduces the amount of resist needed in the coating process and is referred to as RRC, reduce resist consumption. The wafer is covered with photoresist by spin coating. Photoresist is dispensed onto the wafer, and the wafer is spun rapidly to produce a uniformly thick layer. The spin coating typically runs at 1200 to 4800 RPM for 30 to 60 seconds, and produces a layer between 0.5 and 2.5 micrometers thick. Runoff from the extra photoresist is removed through a process called edge bead removal to produce a flat layer of resist. The photoresist coated wafer is then pre-baked to drive off excess photoresist solvent. A mask that resembles the chip's geometry is held above the resist-coated wafer. UV light of extreme intensity is directed downward through the mask and onto the wafer. This causes a chemical change in the photoresist that is exposed to the light by the mask. Developer is then used to wash away certain areas of photoresist. Positive photoresist, the most common type, becomes soluble in the developer when exposed and is washed away. With negative photoresist, unexposed regions are soluble in the developer, and they are washed away. In the etching process, a chemical agent removes the uppermost layer of the substrate in the areas that are not protected by the photoresist. This reveals the silicon wafer to the unprotected areas. After a photoresist is no longer needed, it must be removed from the substrate. This usually requires a liquid resist stripper, which chemically alters the resist so that it no longer adheres to the substrate. Silicon dioxide is deposited onto all regions of the wafer to layer any parts of the wafer that may have been altered in the cleaning process. Silicon dioxide that layers on top of the photoresist is removed and the first layer of the chip geometry is completed. The process is repeated to obtain different geometries at as many necessary layers to complete the chip's circuit design. A chemical agent removes all silicon dioxide from the wafer, and silicon is the only element remaining on the wafer. How has photolithography improved from 1855 to the modern day? The smallest degree of detail, or resolution, that photolithography can be measured by is determined by two factors: the numerical aperture of the optical system and a light source. The numerical aperture can be approximated with the index of refraction and the max half angle of the collimated light as shown in the picture. The index of refraction can be larger or smaller in some cases, and similarly, the max half angle can be altered by a change in focal length or beam diameter. Shorter wavelengths of light generate a lower resolution. The old standard of light source use was a mercury vapor arc lamp with a wavelength of 365 nanometers. The new standard light sources are fluoride-based lasers with a smaller wavelength. Moore's law states that the number of transistors in a space is doubled every 2 years. Smaller resolution allows for higher density of transistors within an integrated circuit. This allows for higher capabilities of computer processing with smaller components. The new standard of critical dimension, the maximum distance between gates on the component, of the transistors is 14 nanometer. Some companies that sell modern industrial photolithography equipment are ASML and Santu. That's the basics. Photolithography. Size matters.
Okay. Is it visible, this slide?
Yes, sir.
Okay. So you have basic idea about the photolithography by seeing this video. So lithography, sometimes it is called photolithography also, is a process by which we can transfer some pattern from photographic mask to a resultant pattern on a wafer. Okay, silicon wafer. So that means transfer of any kind of structure from mask level uh, onto the wafer level is known as photolithography. Okay, so what is the technique? In photolithography process, a photo sensitive polymer film is applied on silicon wafer. Now this photosensitive polymer film is known as photoresist, as we have all of you have seen in this video, last video. So this film is dried and then it is exposed with the proper geometrical patterns through a photo mask to UV light or other radiation, and finally it is developed. Okay, instead of UV light, in some cases we use X-ray also, or electronic beam also, or ion beam also can be used. Okay, accordingly those techniques are known as electron beam lithography or ion beam lithography or X-ray lithography. It depends on the source, light source. So when you use UV radiation for exposing the film, then it is known as UV lithography. And when you use deep ultraviolet rays, then it is also sometimes known as deep ultraviolet lithography. Okay, now depending on the polymer used, either exposed or non-exposed area of the film is removed in the developing process. That means in some cases we will find that export portion of the film will sharpen, it will be dissolved in developer solution. Now in some cases after exposure we will see that this polymer film, which is photosensitive, has been hardened and is very difficult to dissolve in the developer solution. So there are two kind of photoresist. One is positive and another known as negative photoresist. Now the photolithography process requires various uh, chemicals. It requires various gadgets and equipments. Those are namely photoresist, resist, spinner, mask aligner, developer solution, baking ovens, etc. Okay, so photoresists are made sensitive either to UV light or electron beam or X-rays or ion beam. But out of all these lithography, ultraviolet exposure source is very much popular, and UV lithography, ultraviolet lithography, which is very much used in most of the cases where MEMS or based devices or any VLSI process. Okay, it is used. VLSI, very large scale integration process. Very few cases we require ion beam or X-ray lithography, where we need high resolution and is very small picture size. Then sometimes you go for X-ray lithography or ion beam lithography. Now, as I mentioned, there are two kinds of photoresist, positive and negative photoresist. They are complementary to the each other as far as their properties are concerned. Okay, now negative photoresist becomes less soluble in developer solution when they are exposed to radiation. On the other hand, positive photoresist becomes more soluble after exposure. Okay, in this diagram, the positive photoresist, this one, becomes more soluble after exposure. Okay, so here now you can see here the mask is there. This is the mask pattern. Okay, this is the photoresist. This is the thin film which is deposited onto this substrate. This is the silicon on this. This is the film, thin film. Okay, now the transfer of this pattern, this mask, either can be it is used by for positive photoresist, or can be implement using negative photoresist. Okay, so this black is called mask, and when we expose this mask under any UV exposure, then if it is photoresist, positive photoresist, then only this position will not be exposed to the light. Other positions are exposed, so these are weak and these are very strong, so that's why it is remains in this position. Okay, and if it is based on negative photoresist, then only the exposure portion will get strong, and the portion which is not exposed to the UV light, this position will be weak, so this will be eliminated. Okay, so when we etch this photoresist after this one, after this is the first step, this is second, this is third step, so we need to clear, or we need to remove this photoresist, so that under this film, this thin film can be etched. And how this can be etched? If it is based on the negative photoresist, then this portion will be remains same, but this portion will etched or removed after it is inserted into the developer solution. Okay, so positive photoresist become more soluble after exposure. Okay, so what are the various steps?
Sir,
Yes,
sir,
yes.
we have 2 minutes remaining something,
Huh.
and we should stop here, no?
2 minutes. Okay, if it is ended within 2 minutes, after that you have to click on the same link to join again to continue the second session. Okay.
Okay, sir, but I don't have too much charge in my phone.
Okay, those who have any problem, any issue, they can join or they cannot join. But I need to finish my today's lecture. Certain limitation is there. Uh, I have to finish that portion.
Okay, sir.
Okay. If you have any problem, then tell me your name and roll number, and you can leave this class. But I need second session, another 30 or 40 minutes to end my lecture. So what are the steps in pattern transfer? So this is the first step, which is called the preparation of photo mask. So photo mask making, that is the first step. For that you have to have certain information which contains the geometrical feature corresponding to a particular mask, and that geometrical feature is electronically entered with the help of layout edited software. Okay, different, there are various kinds of layout editor softwares are available in the market. Now one such name is Lassi layout editor. Lassi, Lasi in capital, Lasi, Lassi layout editor. Okay, you can design your pattern and electronically transfer onto a mask making machine using that editor software. Then according to the data, uh, the mask making machine will expose onto an emulsion or chromium coated substance, or you can call it as a mask plate. So depending on the data entered into the pattern generator, the mask plate will